Hi, good evening. My name is Raman. I'd like to go over a few graph-related problems. So for this first problem here, we're given a graph, and it is essentially a directed weighted graph. In other words, the edges have arrowheads, and the weights are ascribed to the edges that connect nodes. And so it's asking for us to represent the graph using what's called an adjacency matrix. And an adjacency matrix is, in a sense, a 2D matrix. And you can imagine, of course, since a matrix has rows and columns, you can imagine there being a joint slot between a particular intersection and a particular row and column. And that row and column represents whether or not there's a connection between two nodes. So, for example, here we see that there is a connection between A and B. Now, of course, if that is true, then the convention is to say, okay, well, at row A, column B, put a 1 if in fact there is a connection between them. So we would have put a 1 here, or put a 0 if in fact there isn't a connection, right? So essentially the 2D matrix starts with an array of defaulted zeros. But if there is in fact a connection between a row and a column, and we see that visual representation in the graph, then we put a 1. But since this is a weighted graph, we don't necessarily have to put a 1 or 0. We can in fact put the weight itself, and that would in fact complete the purpose of symbolizing that there is a connection, but it would tell us what the weight is. So there's a connection between A and B. So at row A, column B, put what the weight is, and which in this case is 2. Um, Row A, column, we can also see from this that there's likely a connection between A and C of weight 4, right? And that's, of course, true. There's a connection between A and C, weight 4. So you go to row A, column C, and put a 4. And so that's essentially how this adjacency matrix is built up. We see a connection, D and E. Okay, well, row D, column E, weight 8, right? Row D, column E, weight 8. And that's the way this is done. And so the rest of the adjacency matrix is in fact um, built using this kind of convention. Now, one thing I think is useful to mention is that if you have a graph of n vertices, the size of your adjacency matrix is in fact going to be n by n, right? So in this case, we had 1, 2, 3, 4, 5, 6, 7. Well, in that case, our adjacency matrix was 7 by 7. In other words, it's 7 squared. And that's why they say that the space complexity of a adjacency matrix is n squared, where n is the number of vertices. So hopefully that's self-explanatory. Again, if there's a connection between X and Y, go to row X, column Y, put the edge weight down. If the graph itself doesn't have edges, well then simply represent a connection as being a 1. Now this is another way of representing graphs. This is an adjacency matrix, and in an adjacency matrix, we essentially have an array, and each cell in the array represents a node, and the neighbors, or in other words, the outgoing connections of a particular node, are in fact represented through a list, right? So um, all of the neighbors of a particular node are in fact represented to a list. So you can see here that F has the neighbor G of weight 4, which is actually true. If we go to F, it has the neighbor G of weight 4, and it has no other neighbors, and so that's the only one that appears. If we go to A, well, A has A is connected to B, so B is a neighbor of A, weight 2, and A is also connected to C, right? So and that is of weight 4. So A is connected to C and B, weight 2 and 4 respectively. And that's how the adjacency matrix is built. So what you want to think of it as being a list. The adjacency matrix is an array connected to a list where the array cell is in fact a node and the list represent the culmination of neighbors. Just real quick, if you wanted to talk about time complexity, I told you that when it comes to space, for the adjacency matrix, it's n squared, where n is the number of nodes. Removals, if you wanted to remove a connection, right, you would essentially just make it blank, or um, change it to 0. But in this case, you wouldn't change it to 0. In fact, you're signifying that a connection exists there, which you don't want to do, and it's of edge weight 0, so you don't want to do that. But If you wanted to remove from an adjacency matrix, there's a fixed formula for there's a constant time formula. So you're not really doing a traversal as such, and so it's actually order of one. And if you wanted to add, it's the same thing. It's an order of one operation. If you wanted to, so add is in a sense add a connection between two nodes. Again, fixed time, constant time formula that brings you to the adjacency matrix. So removals and adds are O of one. Um, so you have remove, you have add. If you wanted to find um, all of the incoming neighbors, you would actually have to. You would end up checking a particular column, right? So it's order of n. And if you wanted to find the outgoing neighbors, again, you would check a row, and so that's order of n, right? So like for instance, how if I wanted to judge how many neighbors E has, or what are E's neighbors, or what is E connected to uh, outgoing connections, I would in fact just look at the row here, right? I'd go to row E and I'd say, okay, well, where is this? Where is there a connection? Okay, there's a connection here, A. There's a connection here, F. So in fact, I'm doing a linear. In the worst case, I have to look at each. In fact, I do have to look at each row, or not each row, but I have to look at n elements. So that's essentially the idea. Um, and that's the idea here. So removal's order of one, adding is order of one. Looking at incoming and outgoing neighbors are order of n, and space is n squared. For an adjacency list, the space is order of n plus m, largely because you're storing n elements and then m neighbors. Um, Removals are a little bit more complicated. It is in effect what it would be for the time complexity is what it would be for removing a linked list, an item in a linked list, which you would imagine for a particular neighbor, you would have to go to the amount. In the worst case, you'd have to look for the neighbor that you're trying to delete, which is um, in order of n time complexity, but it wouldn't be n necessarily because you don't necessarily have n neighbors connected to a particular element. You just have however many neighbors there are. And for a directed graph, that would in fact just be the out degree, right? Order of the out degree of that particular node, right? In a sense, you're actually saying order of how many neighbors there are for that node in the worst case. So it ends up being order of out degree, because out degree represents how many outgoing connections there are, and outgoing connections represents how many neighbors there are. But if, let's say, this was an undirected graph, then it would be looking at a culmination of in degree and out degree, in which case it would be order of deg V, where V is the node that you're looking to remove a connection from. So it's either order of deg V or order of out degree V. So depending on what kind of graph you're looking at, that's what that would be. And in this case, it's directed, so it would actually be order of out degree V. So that's removal, right? That's removal, and then that's space. And then adding is actually a relatively easy thing if you wanted to add a connection between let's say C and then let's say another letter of some kind. All you'd really do is it's assumed that you have a handle on this um last node, because with linked lists you actually store the reference to the tail, and in which case you can just simply append that element in constant time. So it actually ends up being an order of one operation. So remove is order of deg v or order of out degree v. Adding is order of one. Um, the space complexity is order of n plus m. And so you have removal. Finding how many outgoing neighbors, again, that's just order of out degree v, or order of deg v in an undirected graph. Incoming neighbors is a little bit more complicated. That, to my understanding, actually ends up being order of n plus m because you actually end up having to look at the entire graph. So there we go. I just put that up here just so it's clear. It is order of degV to find the outgoing neighbors, right? degV in an undirected graph simply meaning that there are outgoing um, edges in both directions. And then incoming is order of n plus m because you really have to look through each list to know uh, what something is connected. What are the things connecting to this, which you'd have to know, which is a hard thing to do, rather than what things is this connected to, which you could just look at the neighbors. Anyways, that the time complexity across both of these questions were not necessarily asked, but frankly, that's an important thing to go through. This is asking a breadth first search. So if you're familiar with a breadth first search, the idea is you have a queue and you start by appending the source to the queue. And so right now your BFS tree looks like this. And the BFS tree is going to be a different looking tree, a tree being a graph without cycles, but it's going to be a different looking tree once we're done traversing this. There are a few things to remember. So you have the queue and then you put the first node in. And um, right now that is A. And A is connected to H, B, and F. So that ends up these actually end up being valid connections to A, H, B, and F, right? And that, in fact, is appended to the queue. So H, F, and A are appended to the queue, but we append them in alphabetical order. So in this case, it will be B, H, F, B, F, and H. And after you've registered all of the neighbors of a particular node, that node is now done processing. And so we can move on from A. Um, and now we're looking at B, right? So B, now we do the same thing with B. So we're looking at B, we're saying it's connected to H and it's connected to D. H is already considered. So the only thing we really have to worry about is D. And so D is now on the stack, or it is now on the queue. And that is where we are with that. Um, since B has no other neighbors, we can remove B from consideration, move on to F. F has no connections, so it lived and died relatively quickly. H is connected to C and E. Okay, well, fair enough. So let's say C and E. So C and E. And um, okay, well, we've processed all its neighbors. H is out of consideration. Let's look at D. D is connected to G. So let's update our graph. And now we have G as a connection. And G is now on the graph, or in the queue, rather. D is now done processing. Let's remove D. C is connected to D. D was already considered before. E is connected to F and G, both of which are considered before. G is connected to nothing that isn't already considered, and so that's removed. And so this is your BFS tree, and the answer here would be A, B, F, H, D, C, E, G. Now, for this next problem, it essentially asks you that while you're performing the DFS, think of this construct where you have something called a maxed differential distance, where that difference is the maximum distance value of any node on the queue minus the minimum distance value of any node on the queue. So while the queue is in processing, there's this idea of something being a max differential where you take the minimum distance that the queue considers or the queue has at the moment with the maximum difference that the queue has at the moment, and then you bid them together and you ask yourself, okay, well, if I subtracted the max from the min, what number is produced, and of everything I could do that with, what is the max yielded from that process? Now, interestingly enough, if you were to actually trace this back, you would find that, and we can do it real quick, right? Um, but if you were to collect their distances, you would only ever find a distance of one as being the max case. because as soon as you, because it's a level by level traversal, so the queue at one snapshot in time only considers um, it essentially only considers two adjacent levels at the most, right? So when we're processing A, right, we're looking at A's neighbors, B, H, and F, and B, H, and F are one number, they are one level away from A, right? No, and nowhere through this process, right? Just think about it. So if we had a queue and we put A in, okay, well, A is connected to B, H, and F. So we're processing A right now, and we find that it's connected to B, H, and F. So B, H, and F. And I mean, really, the idea here is that those neighbors are one level away from A. Um, Now, if you moved on to the next thing, and so this is distance zero, and then these are all distance one. And if you moved on to the next thing in the queue, you would essentially restart that process, right? Where, okay, let me look at B. While I'm on B, okay, well, B is D and H. Okay, well, D and H. D and, uh, well, it would be F and H, right? And now that you're on B, you're looking at B or D and H. Okay, well, H is already considered, D isn't considered, so it would be D, right? Now even then, right, B is distance one, and B's neighbors are distance two. They're one level away. What happened here essentially is true for all levels. It's like a sliding window in a way, where you're moving down, you're essentially moving across a fixed kind of gap, and that gap is in a sense maintained across how you're so it's really only ever one. And it's only, and there's another question that says, okay, well, if it's one, is it one for every graph? And that's true, it is one for every graph, but if in a case where you have only one node, um, if you only have one node and you put that in a queue and then you process its neighbors, it's distance zero from itself. You process its neighbors, and I mean, then what, right? Then you remove it, and zero was really only that was in fact the minimum of the max differential. So if it's a graph with more than one node, then it'll be one. The max difference will be one. If it's a graph with exactly one node, well, then it'll be zero. And if it's a graph with no nodes at all, in which case it will also be zero. Um, it might be even, if you have a graph without any nodes, you might also even consider to say that it could be null, not zero or one, but it in fact could be null, which is a little bit abstract, but it depends on, what your definition is, right? Those are the graph related questions, and I'm happy to have gone through them. And I really had a lot of fun working through these problems. Thanks again.